the intuition behind this type of optimization problems is so important for the rest of the course that I want to develop some additional economic intuition for you. So we have seen in the previous segment of the video that in many economic problems, the benefit function has this shape as a function of x, with the derivative being greater than 0 and the second derivative being less than 0. Notice, as a side note, that that implies that the benefit function itself is a strictly concave function. Now, why would that be the case? When would you expect the benefit function to have these properties? The idea is that in any situation in which every additional unit that gets consumed improves the benefit that we get, you will have a positive slope, but that the first unit has a much bigger return, a much bigger benefit than the second. So notice that this is the benefit of the first, of the second, of the third. It keeps getting smaller. So in other words, the benefit, the additional benefits, the marginal benefits keep getting smaller. Any situation that looks like that will have this pattern. And there are many situations that look like that. Imagine, for example, and this is something that has been documented by psychologists and neuroscientists, that you are eating an ice cream, and the first spoonful of ice cream that puts in your mouth, especially if you're hungry, or especially if it's very hot, it tastes like heaven. The second spoonful that you put in your mouth tastes very good, but not quite as much as the second. And unless you are like myself, by the 100th spoonful of ice cream that you put in your mouth, the marginal additional pleasure that you get is very small. That is something that has this decreasing pattern, if you think as benefit as the pleasure that you're getting from the ice cream. Now, there are some economic situations in which the benefit function is linear. It looks like this, okay? So this will be b of x, and in this case, b of x will be greater than 0, and b double prime of x will be equal to 0. This is a situation in which every additional unit will generate the same additional benefit. And a typical example of this is in the case of the firm. So as an example, in the case of the firm, when the benefit is revenue, so is equal to the price of sale times how many units have been sold, this is a linear function with slope p. So I hope that this gives you an intuition for why in many circumstances the benefit function is either linear, in which case the second derivative is equal to 0, or has this strict concavity property so that the additional benefits of taking action X keep going down and down with subsequent actions. In order to pass you the intuition for the case of why the costs look like they do in many economic problems, I want to add one tool to your tool belt that will be very useful throughout the course and for getting that intuition. Remember that the case of a strict concavity the function looks like the inverted ball, is something like this, and that the second derivative has the property that is less than 0 at all x. You can think of a strict convexity, a function that looks strict convex, as something that has basically the flip form. So a strictly convex function will be one that looks not like an inverted ball, but actually like a ball that can hold water, and in which the second derivative is greater than 0 at all x. It's just the flip side. I hope that the intuition is clear. The intuition for why the costs are convex in many economic problems is very similar or very analogous to the case of the concavity of the benefit function. So we can go through it a little bit faster than before. Consider first a function, a cost function that looks like this. This is a case in which the cost function has the first derivative being greater than 0 and the second derivative being equal to 0. It's linear, okay? A typical example of this will be one for a consumer in which the cost of buying X unit of computing power in the previous example is P times X. So the cost increased linearly with a slope of P. Now, These functions that are linear, are convex, but not strictly convex. There are also many economic cases in which the cost function may look like this, in which case the first derivative, as before, is greater than 0. Every additional unit of action x that gets taken costs more money, but the second derivative is greater than 0. In other words, every subsequent unit that gets produced, notice how the slope is increasing, costs more and more to produce. Now, in this particular case, the C function is strictly convex. Convex is like a ball looking up. And a typical example that takes this form is, for example, for a firm that produces through resource extraction. Suppose, as a motivating example, that you are a firm that sells rare rocks. Finding the first rare rock to sell is relatively easy, maybe just sinking in the surface with a marginal cost of 0, but finding more and more rocks as your level of production increases the cost more than linearly.